Our first talk this afternoon will be Cycles, Tools, and Cohomology Theories by John Morgan.
Well, it's a great pleasure to be here. Can you hear me? Oh, it's a great pleasure to be here. Can you hear me now? Especially in the conference in honor of Lefschetz. I met Lefschetz a couple of times. I had a few very slight conversations with him. He once gave me a check for $10, which I never cashed. Held on to it, but that was almost 65 years ago, and it's long gone, right?
Worth how much today?
So even though I never had a serious mathematical conversation with him, he influenced my mathematical trajectory deeply. I spent a long time early in my career trying to read the article that Carlos alluded to, analysis thesis and geometry Creek. Not much avail, actually. I learned a lot, but I was trying to understand if his argument for the Hard-Lefschetz theorem was really right or not, and I got nowhere. But what I learned, the vanishing cycles of the Hard-Lefschetz, the vibrations of algebraic values by curves, which we've been hearing about in variations through all these days, just incredible mathematics, and its influence continues today and throughout algebraic geometry. Anyway, I decided that rather than talk about the various times I've planted a little fishhook of algebraic topology in the whale of algebraic geometry, I would talk about some of the other part of Lefschetz's work, which was back in pure topology. And I want to talk about the subject that revolves around Poincare and Lefschetz duality, the purely topology of algebraic geometry. I will start with the context where the questions that Buddy came from, then talk about Poincare duality and Lefschetz duality in very direct and down-to-earth terms. And then I'll move from that to a construction of a Bordism theory that has, to me, the invariance of the Lefschetz invariant coming from Poincare duality. And then if I have time in part 4, I'll try to tell you about the reason that I did all of this. Though I think the Bordism theory is beautiful in its own right, I had a reason to do it, which was to give a better proof of something that Dennis proved more than 60 years ago. I thought Dennis's proof.
That's not making it to the back.
Is it something I'm doing? Is that helping? So, move it up, or you want me to talk louder?
Maybe talk a little bit.
Can I talk louder? I don't know, I can try.
Okay.
Anyway, the reason that I was motivated to do this was to try to give a different and to me more natural proof of something that Dennis proved in the 60s, very important and crucial part of surgery theory. I don't think Dennis liked his proof either, because I know he looked for other proofs, and this was my version of what I considered the right way to do it. Never thought of this idea until I heard of traverse homology, intersection homology, and traverse sheaves. And then as soon as McPherson came to IGS in the spring of '76 and talked to us about intersection homology. It was clear what to do. I think we discussed it at the time. Anyway, let me start with the context. To me, the context here goes back to, I said Poincare's question, it's Steenron's question, sorry, that's a mistake. And then I'll lead from that to what I mean by cycles dual to cohomology theory, and a particular statement which goes under the name of Anderson duality, connecting homology and cohomology theories. So again, it's Steenron's question. Must be a question from the 50s. Every homology class represented by a manifold. So if you have a homology class in space X, can you find a manifold of the same dimension as the homology class's oriented manifold? So that when you map the manifold in, your class is the image of the fundamental class. Okay. Well, there's a beautiful answer to that question. In fact, there are two beautiful answers, both by Owen and Tom. If you're willing to work up to odd multiples, you can always represent the class. But if you really want to represent the class, the answer is no, you can't. And interestingly enough, both answers come out of the Steenron algebra. The first answer was from a complete understanding of the structure of the Steenron algebra and the resulting structure that it gave you for Bordism. Tom was able to give the first positive answer. The second negative answer comes from using the analog of Steenron squares, the so-called peak powers at odd primes, and those turn out to be obstructions, or rather the dual homology operations to these cohomology operations turn out to be obstructions to representing a homology class by a manifold. And I have a picture of this, if I can put it up. So let's think of our space X itself as a manifold with a Morse function. It's a little easier to think about, so that totally doesn't matter. So here are all our levels, starting down at the bottom with the points of index 0, and here we're working up in some dimension. We have a cycle. So it will be a linear combination of handles with coefficients. That'll be the chain that, let's say it's a dimension K, that represents the cycle. And now this is a manifold with boundary, and I want to try to extend the manifold downward through past the lower critical points. So at the first step, it's easy. If you look at one of the critical points in one dimension below, so K minus 1, it has an ascending manifold. If you intersect these disks, the descending disk with this ascending manifold, you'll get points. You have to count them with sign, but the fact that you're starting with a cycle is exactly the statement that all those signs add up to 0. So for example, you might have these two guys would both meet this ascending manifold in one point. We could then extend it down like that to get it up a little bit and push our manifold down past these critical points. So you get past the codimension 1 critical points because you started with a cycle, not an arbitrary chain. As you go lower, at each stage you have the same problem. You intersect the manifold you built, maybe it goes down to here, with these ascending manifolds from the next critical points, and you'll get submanifolds inside this boundary which you're building. If those submanifolds bound, then you can do exactly what I did here. Use whatever this manifold bounds to push it down through the critical point, take a neighborhood, and push past. So if manifolds always bounded, you could continue to do this forever. But of course, manifolds don't always bound. And the first time this process runs into trouble is when you get down here at the K-5 level. You see this? So these critical points. So the ascending manifolds of these critical points will meet the descending manifold you manage to construct in four manifolds. Those four manifolds can have a signature. So you end up with a chain, the tensor product of the classes of those four manifolds times these codimension 5 handles. If that is a boundary, you can continue the process. But if that, it's always a cycle, it turns out, geometric reasons. If that cycle is homologically non-trivial, you're stuck. Because this is the first obstruction, it's well defined. And that is one of these steam rod P patterns. Just giving you a geometric picture of it. You find a space where that operation is non-zero, this process is going to stop right there at codimension 5. And to continue it, you'll have to put in some essential singularity. That was Tom's argument using the steam rod towers. Anyway, that's part one of our context. So what does represent homology classes? Well, so tautologically, what represents them is pseudo-manifolds. These are simplicial complexes that every simplex is a face of a top n-dimensional simplex. The n-dimensional simplices are oriented, they meet pairwise in their codimension 1 faces, and they make a cycle. So every pseudo-manifold has a fundamental class, just like a manifold was almost by definition. And on the other hand, every pseudo-manifold is the boundary. You can talk about pseudo-manifolds of a boundary where you have, again, n-dimensional simplices. Either they meet their faces, codimension 1 simplices that are faces of 2, and then some codimension 1 simplices that are faces of only 1. That makes the boundary, which is a pseudo-manifold of 1 dimension less. And every pseudo-manifold bounds, it bounds the cone over itself. So if you can connect a Bordism theory out of pseudo-manifolds, and the Bordism groups of a point are Z in dimension 0 and 0 in every other dimension. So it has the same coefficients as ordinary homology, and not surprisingly, it is ordinary homology. So that's a, shall we say, Bordism theory that represents ordinary homologies, or tautologically. There's not really much interest here, but I just wanted to show you this simplest example. Now, this is an example, well, homology and cohomology are an example of what's called Anderson duality. This is duality between cohomology, extraordinary cohomology theories, generalized cohomology theories, and generalized homology theories. So you need a pairing between cohomology classes in K and homology classes in H. That pairing would, the first instance, give you a homomorphism from K into the homomorphisms from H, coefficients in Z to Z, but we'll tensor with Q, and we'll take coefficients Q mod Z, and we'll get homomorphisms from every element in K will give me a homomorphism from the homology in H with coefficients in Q to Q, and homology of X with coefficients Q mod Z to Q mod Z. And these homomorphisms have to be compatible as indicated by the lower diagram. If that gives you an isomorphism between the K cohomology of X and these diagrams in the H homology of X, you say H is Anderson dual to K, or K is Anderson dual to H. Notice, by the way, that if H is a generalized homology theory, then this group of diagrams is a generalized cohomology theory, simply because Q and Q mod Z are injected groups, which are short exact sequences. So that's the definition of Anderson duality, and we've already seen an example. Homology is Anderson dual to cohomology. If you want to know what an integral cohomology class you have, if you want to identify an integral cohomology class, you can do it by evaluating it in all integral cycles to get an integer and all Z mod n cycles to get an element of Z mod n. You need both. To evaluate an integral cohomology class on an integral homology class, fine, that will tell you about what it is mod torsion, but a torsion homology class, cohomology class evaluates trivially on every integral homology class. You need to work with the mod homology as well, and that's what those diagrams are about. Anyway, Anderson homology is Anderson dual to cohomology, and I just reformulated it as a pseudo-manifold. The Bordism is Anderson dual to cohomology. So this is a very trivial but paradigm for a great answer to cycles dual to a cohomology theory. Two pieces. One, you'd like the cycles to be geometric objects, not formal, like the cohomology theory. You want them to have geometric meaning, and in the best possible case, those cycles would make a Anderson dual theory. So that, as we will see, not always directly what you get. I want to give you one other example. It's a beautiful example. It goes back to Connor and Floyd in the 60s, and it was relevant, or a slight version of it was relevant. And this is original proof of the theorem that this will be a different proof of it. And this is the complex Bordism. So Bordism of stably complex manifolds can be used as cycles for complex K theory. Connor Floyd. So we begin with mod periodicity. So we have a complex line bundle over some space X, and we split the exterior algebra on that bundle into two complex bundles, the even exterior algebra and the odd exterior algebra. We pull those bundles, which are now defined over X, back to the total space of E. So we get these two bundles, pullback bundles over the total space of the original vector bundle. And away from the zero section, they're isomorphic. In fact, at any non-zero point of the vector bundle E, we can just wedge with that element to get an isomorphism between the odd tensors, the even tensors to the odd tensors. So we have two vector bundles over the total space of this vector bundle, and away from the zero section, an isomorphism between them. So this produces a relative element in K theory, or if you like Tom spaces that I do, it produces for you a cohomology, reduce the cohomology K theory class in the Tom space of E. You can think of it as the compactly supported cohomology of E, or the cohomology of a disk bundle inside E modulo the sphere bundle, however you want to think about it. Anyway, this class has the property that if you restrict to one fiber, well, when you compact the fibers in the Tom space, you get spheres. These are even-dimensional spheres. Reduced K theory of the sphere is the integers, mod periodicity. And the condition that this class satisfies is restricted in any class, it's the bot class. So it is the generator of the K theory of any one of these spheres complete with fibers. And then that means it gives a Tom isomorphism for complex K theory for complex bundles. So for any complex bundle E over X, you get an isomorphism from the K theory of X to the reduced K theory of the Tom space just by picking a class in the K theory of X, pulling it back to the bundle, and then coupling it with the Tom class. That's the Tom isomorphism of K theory. So that's mod periodicity. So a stably almost complex manifold is simply a smooth, even-dimensional manifold that has a given embedding in a much higher dimensional sphere whose normal bundle has a complex structure. So the stable normal bundle emits a complex structure and we choose one up to. So we're now going to make a Bordism theory based on these manifolds, and it's called capital omega mu. So we're mapping these almost complex manifolds into X. Using this Bott argument, Bott periodicity, Conner and Floyd defined a map from the K theory of X into the homomorphisms from the mu Bordism, the almost complex Bordism, into X. The way they did it was take a cohomology, take a vector bundle, the element K theory, and take a representative of almost complex Bordism, that's the F from M to N, and form the pullback of the cohomology class from X to M. That gives you a K theory class. That gives you a K theory class in M. Couple with the Tom class of the normal bundle of M, and you end up in the reduced K theory of the Tom space of the normal bundle. But the normal bundle of M is the normal bundle of an embedding of M in the sphere. So this Tom space, well, before you collapse out the boundary, if you take a tube around the embedded manifold, maybe I'll draw a picture. I have this huge sphere, and inside the sphere I have this embedded submanifold. I take tube, which is like the disk bundle of the normal bundle inside this sphere. I now have a K theory, a relative K theory class on this tube mod its boundary. Well, that extends by 0 outside to a K theory class on the sphere. It's just the pullback under the degree 1 map from the sphere to the Tom space of this element I have.
You have the isomorphism between the two pieces, so
Yeah,
you sort of zero away from the zero section.
that's right. 0 away from the tube is a relative class inside the tube. So that is an extension of this relative class on the Tom space to a K theory class on the sphere. But this is an even dimensional sphere. It's K theory again. It's a reduced K theory class is Z. So you end up then with this gives you a pairing between the class alpha and the representative of complex Bordism F from M to X gives me an integer. So that's my function rho of X. Rho of X. Did I write it down? So rho of X is the pairing between an element in K theory and a complex Bordism element given by the formula F star alpha of the class pull back to the sphere, which is the integers. Sorry about that. Anyway, the basic property this class has, the Riemann-Roch type theorem, is that if your complex Bordism is given by taking a product of two manifolds M cross N, then projecting onto M, and then mapping M in, the relationship between the value of the invariant for the composition and the value of the invariant over M is you multiply by the Todd genus of the other manifold. So as I say, it's the Riemann-Roch. So we're not getting Anderson duality between the K theory of X and the homomorphisms from the Bordism to Z, because we have all these relations among the Bordism. I say when you multiply a Bordism element by another almost complex manifold, then project that in, that's not independent from the value of one of the factors. So what it means is that this map from K theory to the homomorphisms actually factors through a quotient. So it gives a homomorphism on the Bordism, the mu Bordism, but that homomorphism factors through the tensor product over the Bordism of a point the mu bordism of X, and the integers for the action of the bordism of a point on the integers is given by the tangents. So in fact, you end up with a map like that. And Connor Floyd proved that this is an Anderson dual map, or rather the extension to Q and the Q minus Z version of this. What's actually fairly the non-trivial part of this theorem, besides spot periodicity, is to know that what's on the right-hand side is an extraordinary homology theory. That's not obvious. It's not true in general, but special properties of mu, like its homology tree and so on, allow you to prove that is a homology theory. If you calculate its value on spheres, you see you get the same answer. So if it is a homology theory, it's got to be K theory. But to work a little bit to prove it's a homology theory. So this gives us an answer for K theory to the original question. What are the cycles for K theory? What are cycles for K theory? Well, these almost complex manifolds, in one extent, are good cycles, because if you know the value of your K theory class on every almost complex manifold, as given by this homomorphism, that determines, both with integral coefficients and Q minus Z coefficients, that determines your K theory class. But it's not an Anderson duality, because not every homomorphism comes from K theory. None of these homomorphisms that factor through this quotient. So the Anderson dual theory is a quotient of a geometric theory. And, so this actually is a pattern that there are quite a few results along these lines. In fact, there are other versions of Connor-Floyd isomorphisms that involve real K theory, KO theory, symplectic theory. They get mixed in a funny way, unitary, special unitary theory, all have versions of this kind of isomorphism for different kinds of K theory. Okay, that's our introduction. You know, cohomology theories, you look for cycles on which you can evaluate these cohomology theories, some pairing, and maybe you get an Anderson dual theory, or maybe there's some relationships, product formulas, you have to pass the quotients. These are the kind of answers that we're looking for. So now that's the end of the introduction, which was to set the context and has very little to do with everything else that's going to come. Now I want to start talking about duality, Poincare duality, Lefschetz duality, and this beautiful, I think it's due to Dali, but it's so obvious that it's the kind of thing Miller might have thought of 50 years ago. It's just, when you hear about it, obviously this is the way to do it, truncation. Okay, but let's start with duality, Poincare duality. So, unlike most of you in the room, I care about torsion. I'm a topologist. So, to me, it's not just rational cohomology or complex cohomology. I care about the torsion as well. So, when you think about the torsion, you have to divide it into two cases. I want to associate to a space or a manifold with boundary. Well, I have its homologic cohomology, which I'll call H upper K. The free part of its cohomology is the quotient by torsion, and the torsion part I'll denote by TK of L. Well, these are the objects that have pairings under Poincare duality. As we all know well, the free parts are paired. But the torsion parts are also paired because I'm working with cohomology rather than homology. The pairing and torsion, the sum of the dimensions is one more than the dimension of the manifold, takes values in Q mod Z. These are perfect pairings in both cases. They pair either one with the homomorphisms of the other to the other side. And there is one particular, among all these pairings, one that's a self-dual pairing, which is much more interesting. You have two different things that are paired, and that's okay. But if you have something paired with itself, it's a lot more structured. If the manifold is even dimensional, again, the very familiar case, the middle dimensional free part of the homology has a self-dual pairing, which is either symmetric or anti-symmetric, whether it's dimension which is 0 or 2, 1, 4. When you have odd manifolds, it's a torsion pairing that's self-dual. If you have a 2k minus 1 manifold, you have the K cohomology torsion tensor itself to Q minus C, and it has, again, a symmetry. Dimension 4k plus 3 is a symmetric linking pairing, and dimension 4k plus 1, it's a skew symmetric pairing. Similarly, there are Lefschetz dual pairings. We have an n plus 1 manifold with boundary. The boundary is L, and you get a pairing between the absolute cohomology and the relative cohomology, preserving the dimension, and between the absolute torsion and the relative torsion. Again, you have to up the dimension by 1. And of course, these all fit together. You have the log exact sequence of a manifold with boundary. I put the boundary in the middle here. This is a self-dual sequence, which is a little complicated to say because you've got the mixture of the free part and the torsion part, but in the obvious sense, which you can figure out if you think about it for a few minutes, this is a self-dual sequence. So in particular, I want to concentrate on the middle dimensional self-dual part of the boundary. If the boundary is even dimensional, it turns out the image from the free part and half the dimension of the boundary into, the manifold that bounds into L is a finite index in what I call a Lagrangian subspace inside the free part, the middle dimensional free part of L. And Lagrangian means here that this pairing restricted to A is self-annihilating. So A tensor A goes to 0 with the pairing, and then A is isomorphic under the pairing to the free part modulo A. Always what I'll mean in both cases. In dimension 4k minus 3, the image from the manifold that it bounds intersected with the torsion, that should be K, not K minus 1, is also a Lagrangian subspace for the torsion pairing. It's a torsion subgroup on which the pairing is trivial, and so that the pairing between this thing and its quotient, that Q minus C, is an isomorphism. Now, of course, as we know, the manifold of dimension 4k has a signature, which is simply the index of this symmetric unimodular pairing, and this invariant vanishes. The signature is 0 if and only if there's a Lagrangian subspace with a pairing. So in particular, again, as we know well, if L is the boundary of the W, then the manifold W, then the signature is 0. There's a similar result in dimension 4k plus 1. Torsion pairings, the dimension skew torsion pairing, so those in dimension 4k minus 3, have a Z2 invariant, which for reasons I've now forgotten, we call with like when the wrong invariant. We're almost to study these pairings. So this is a Z2 invariant of these skew symmetric torsion pairings, and it is the obstruction to a Lagrangian torsion subspace for these pairings. Just to give you an example of a pairing with non-trivial de Rham invariant. Geosymmetric pairing with non-trivial de Rham invariant is Z12 tensor Z12 into Q1Z. It sends the generator X, non-trivial element, non-trivial pairing, and it's skew symmetric because a half is minus a half. These pairings don't have to vanish on like the interval of skew symmetric pairings vanish on each class. And so this obviously, well, this says de Rham invariant one. It doesn't have any Lagrangian subspace because its order isn't a square. That's the example. So we have two invariants of Poincare duality, and they are invariants of Poincare duality modulo Lefschetz duality. Because if you have something that sits in a Lefschetz sequence, it has a self-annihilating subspace, either in dimension 4K, so a signature is 0, or in dimension 4K minus 3, it has a Lagrangian subspace, the torsion pairing, so it's invariant as also. What I'm going to do is build a Bordism theory, geometric theory, though it be interpreted a little bit loosely, geometric theory, whose Bordism groups are exactly these groups. Z in dimension 4K, Z mod 2 in dimension 4K plus 1, and 0 in the other dimensions. So that for the Bordism of a point, the invariants that detect these homotopy groups are the signature and your own. So that is what I call duality Bordism theorem. So the construction, so this is where intersection homology comes in. The construction uses a variant of intersection homology. So the objects in this theory are going to be stratified spaces, so they'll have singularities, but fairly restricted kind of singularities that come from stratified spaces. Together with, over these spaces, you have an object in the derived category of associated with abelian groups. So we have sheaves of abelian groups, complexes of sheaves of abelian groups, up to chain homotopy and the inversion of quasi-isomorphisms. So we're going to have objects like that, and you can actually take them as, if you want, complexes of injective sheaves, but we're really working in the dual category. So these are going to be objects with complex of sheaves over it. So I like to think of this as being like, what's an orientation for a manifold? An orientation for a manifold is extra algebraic data, fairly trivial. What's a almost complex manifold? That's even more extra data. It's this complex structure on the tangent level. Well, here our extra data is in terms of an orientation sheaf or a self-dual sheaf, which generalizes the usual orientation on the open subset.
Great.
Sorry.
Graded groups.
Well, no, sheaf of the grading is in the sheaf. It's a complex of sheaves. So there's the grading in the sheaves, sheaf of degree 0, degree 1.
It's a sheaf of complex.
No, and each sheaf is a sheaf of abelian groups.
Oh.
They don't need to be graded. So if you were to, over any open set, take the sections over that open set, you get a chain complex, co-chain complex. The germ, the stalk at any point is a complex of abelian groups. So the first restriction on this sheaf is that in the stratified space is a big open subset, which is a manifold of top dimension. It's implicitly always an oriented manifold, and the sheaf there is just the constant integer sheaf that goes with that orientation. So that on most of the space, they're restricted to be that. And these sheaves are going to satisfy a local form of, what I think of as a local form of the Anderson duality, which goes under the name of Verdier duality, which exists in many different categories. But here it's for these complexes of sheaves of abelian groups. I'll just say a word about that. So this is Verdier dualizing sheaf. It's a fantastic thing. I lived a long time in my life without knowing about it, but now I can't stop thinking about it. It computes. So this is sheaves of abelian groups, complexes of sheaves of abelian groups over topological spaces with reasonable properties about their singularities, cohomological. This is a complex of sheaves. We can write down explicitly how you make it, which calculates the Borel-Moore homology of the space. So its stalk at any point is the local homology of the space. Homology of U, we're using neighborhood mod U minus. So this is a complex of sheaves that calculates well, the relative cohomology of U, comma U minus the point. They're just the local homology at the point. So it's picking up the singularities. If your space were a manifold, this would be a constant sheaf Z, concentrated actually in dimension minus n, the way that. But it picks up all these singularities, and this is what allows you to do duality. This is a local version of Anderson duality. Anyway. So our duality sheaf will have the property that if you take the global sections over any closed object, you will get Poincare duality. If you take the global section, you've got a complex that has Poincare duality. You take the global sections over a thing with boundary, with relative boundary, you'll get Lefschetz duality. And if you work locally, you will get the pairing between cohomology and locally finite homology. That would be an isomorphism.
What is it?
I'm going to tell you. Well, little by little, I'm going to try to tell you. So let's think about the local question around the simplest possible singularity in this theory. The first thing you have to think about is I have some closed manifold, L, some dimension I'll put down in just a minute, and I'm going to study the cone over L. I want to try to make a duality. So L is part of the open manifold part. So here I'm just going to use something that calculates the usual cohomology of L. But I have to figure out what I'm going to put here on the cone on L. This is the cone point. So I need to know what's the cohomology of this cone, and then what's the relative cohomology. So there's our sequence. And I've tried to indicate that I know what the cohomology of L is. L's out in the smooth part, so it's just the usual cohomology. I don't yet know what I'm supposed to do over the cone and then relative to the boundary. But somehow I want to extend.
H is the thing you're trying to.
Yeah, so the curly H is the cohomology of the thing I'm trying to define. I have to define it at a sheaf level, but that's going to be its cohomology. Well, there's got to be a self-dual sequence. And you think about L, it bounds lots of different manifolds, probably. So there's a million different sequences that you could put here. You had a question?
What's the meaning of self-dual sequence?
Well, in this case, it will simply mean, well, as we're going to see,
No, what's the definition?
that the cohomology for L has to be dual to the cohomology for cone L mod boundary. You have have the Lefschetz duality between those two, compatible with Poincare duality in L. Anyway, we're going to solve this problem in a very easy way that can be clear what it means. Okay. Well, a priori, there's no obvious canonical way to do that, but in fact, there is a very natural way to do it. And it turns out the very natural way to do it is the correct way to do it because it works for the whole theory going forward. And this is Deline's truncation. So the sequence has to produce, well, okay. I've already said, I've got to have a Lagrangian subspace in the middle dimension, the self-dual part of L. So I'm doing the case here, I guess, where L is even dimensional. So here's Deline's truncation at the level of cohomology. You truncate the cohomology, we're going to truncate in the middle dimension. So you take everything below the middle dimension, you take all the cohomology below the middle dimension. In the middle dimension, I've picked out a self-annihilating, a Lagrangian subspace in the free part of the homology. I pull that back and take all the homology that maps to that and to the quotient. So I take all the torsion plus this much of the free part. That's what I do in dimension K. I call it S tilde being the preimage of this subspace.
Said pull it back, what do you mean?
Well, there's the quotient map from the homology to the free quotient.
Oh.
I have S in the free quotient, I simply take its preimage. So I can add all the torsion. So that's what I do.
You have a Lagrangian quotient.
That's right. That's where the Lagrangian was defined. So below the middle, I take everything. In the middle, I take all the cohomology that projects into the quotient map of the free quotient to S. And above, I take nothing. So what do I get for, just from the long exact sequence for the cohomology now, the relative cohomology? Well, this cohomology injects, so I just take the quotient, which goes under the name truncation from above, everything above S. So in the middle, I'll have the homology mod S tilde. Above the middle, I'll have everything. And now it's clear those are dually paired. You got everything below the middle on one side, everything above the middle on the other side, those are dually paired. If you think about the torsion right near the middle, that works too. So this is the sequence we're looking for.
Maximum Lagrangian subspace.
You have to choose one. Now, there may not be one.
You choose a maximum one.
Yeah. When I say Lagrangian, I mean maximum. Because I require it to its quotient, it pairs dually with its quotient. So this is what the answer's got to be in cohomology. I have to figure out how to do it at the level of sheaves.
So this is not a definition, this is just a motivation.
That's right. That's right. This is what we're aiming for. So I start here, I take an injective resolution of the constant sheaf over everything except the cone points. Everything except the cone points manifold has the constant sheaf, which calculates its cohomology. And now I work in the dry category, I take an injective resolution. There's two obvious extensions of that complex over the point. One is to extend by 0, it's called J over shriek, and that would calculate the relative cohomology.
Calculate what?
The relative cohomology.
Mod point.
Mod, yeah, well, mod a neighborhood. The other thing I can do is just push forward naturally R lower star, as my algebraic geometry friends like to do it. And that simply makes the cohomology of the cone equal to the cohomology of the open. So those are two extremes. One would give you a relative cohomology, the other gives you the absolute cohomology.
Relative, what? Relative.
Yeah, so the trouble is here, I just have the link. Let me,
Cone mod L?
yes.
Okay.
Yes.
Cone mod L, okay.
So this is what my cohomology sequence is supposed to look like. There are two natural extensions, as I said, one to extend by 0, or the other is to take R J lower star J's the inclusion. But neither of those gives us the right answer. One puts everything. Rather, Deline's truncation, which I talked about in terms of cohomology, works as well for the sheaf, for the complex of sheaves. So if you want to truncate a complex of sheaves at some point relative to some cohomology group at that level, you simply take all the complex below that point. In this level, you take the cycles, you take the kernel of D, and only those cycles that project to whatever cohomology class you're interested in. So when you do that, the cohomology of the truncation is the truncation of the cohomology. So this commutes with taking cohomology. So that's what you do. You take, so I put down the two extensions. C is the sheaf I have, the resolution of the integers over the big open piece. The first sequencing, C1 is the extension, what's going to exist over what I'm constructing over the cone. So I could take the RJ lower star and kill off everything above S, and I'm left with the sheaf that I described. The other way to describe it is to extend this sheaf by 0 and then add in over the point all the stuff that sits over the point that's less than or equal to S. These give the same thing. So this is a way to extend this complex, injective complex of sheaves to sheaves over the cone. And it's a little more interesting if you extend and not just think of locally around the cone. Suppose that L is actually the more manifold down here, W. Now you do exactly the same thing. This is all out in the top stratum. So we're just taking some injective resolution that calculates ordinary cohomology away from this point. And now I do the same thing over the point. I don't take the full RJ lower star restricted to this point. I take only half of it, the half that's less than or equal to this self-analysis associates. And because I arranged that the L mod the cone satisfies duality, you take cohomology, W mod L satisfies duality, Lefschetz duality. You put these pieces together, you get Poincare duality. And in fact, the sheaves are self-dual under variant duality. So this is, if you will, the simplest case where your stratified space is made of two pieces, a smooth manifold, a point. Now it's pretty clear what to do when the stratified space has two strata. Do exactly the same thing. Here's the lower strata. It has a neighborhood. It has a Can you hear me? We're all in talking to the microphone. So now I have a two stratum space. Here's the lower stratum sigma. singular stratum. Here's its neighborhood, which is part of the stratified space theory, has the neighborhood is a cone bundle, cone over some length L, locally trivial cone bundle over L, and now here you have a nice manifold. That'll be your two stratum space. We have this same constant integer sheaf away from the lower stratum, or an injective resolution of it. We do exactly the same push-pull reconstruction. The same symbols now make sense, where I lower star and I upper star refer not to the cone point, but to all of the lower stratum. And once again, you have local duality in these little locally trivial boxes, because you forced it on the link direction, you have it in the usual duality in the stratum direction. Now here you have duality, so the whole thing will satisfy
Can you
duality.
make any assumption about transversal geometry or something?
No, well, yes, I'm taking, let's say, Whitney stratified space. Anyway, all I need is local triviality. And then I need the S, the sub thing inside the cohomology, to be locally constant. So this is more than just there exists one for one L. It has to be locally constant around the stratum. Yeah, so that's what I need. All right, well, that's one stratum, two strata. Let me just say that in general, you do the same thing. You extend one stratum at a time over the next stratum. As you're going to extend over another stratum, this link that you have lies in the previous thing where you have duality, so it will satisfy microduality. So this Lagrangians make sense. You need them at each stage in order to complete the construction. Talk about all of this. And now I'm just saying here, you do the same thing one stratum at a time. You prove inductively that if you can make these extensions, which depend on the existence of these locally trivial Lagrangian subspaces, that closed objects will satisfy microduality, and objects with boundary will always satisfy Lefschetz duality. And it's almost tautological that the Bordism group of a point that you get are given by the signature in dimension 4K and the Duran invariant in dimension 4K plus 1. Because if you have an object of dimension 4K or 4K plus 1 and that invariant vanishes, then its global perverse homology has a self and has a Lagrangian subspace. And therefore you can take the cone over it and extend the sheaf using that Lagrangian subspace at the cone point. Dimension 4K plus 2, Lagrangian subspaces are automatic. Dimension 4K plus 3, use the fact that every torsion pairing exists on a 4K plus 3 manifold of bands. So you can add that in.
Start with a pseudo-manifold.
Start with,
Pseudo-manifold.
no, start with an honest manifold. Start with an honest
Well,
manifold.
when you have a stratified space.
Yeah, but I'm starting on the open subset that's a manifold.
No, but are you assuming anything about it's just stratified or it's not a pseudo-manifold?
No, it doesn't have to be. I mean, these duality statements
Okay,
are good anywhere. You have a closed subobject of an open thing, it will, if it's a substratified space, it will satisfy the duality. So these are the right coefficients to be dual to G over top, which has homotopy groups Z in degree 4 and Z2 in degree 4K plus 2. And I don't think I'll say anything else about that, except that the pairing between the Z2s is this product formula that you and I discovered relating the Duran invariant of the box time across the Rivera manifold. You need that paradigm.
All right, well, I won't try to tell you more about surgery.